My name is Grace Strick. I'm a senior engineering student graduating in May 2020 with a degree in mechanical engineering and a minor in computer science. I'm originally from southern New Jersey, where I grew up with my parents and my sister, but I've called U of M in Michigan my home for the last 4 years. Freshman year, I joined Michigan Electric Racing, a project team that builds an all-electric race car. I've been a member of this team ever since, and it's been one of the most rewarding experiences of my time at U of M. It's through this team that I completed my honors capstone project. My capstone revolves around composite structural analysis. In my case, I considered composites of carbon fiber and epoxy. Components made of carbon fiber and epoxy are typically much lighter than those made of metal, but the material properties are a lot more complicated to analyze and simulate than those metal products. For my project, I wanted to help Michigan Electric Racing better understand the material properties and strengths of carbon fiber epoxy composites.
As I just mentioned, I've been a member of Michigan Electric Racing during my 4 years at U of M. We are a multidisciplinary student design team that designs and builds an all-electric formula-style race car for competition. These two pictures are a car last year, and this is just to give you some more context into how I've spent my time at U of M. On that car, you could see the outer surfaces, and those were all of our composite parts. But some composite basics. So the composite material is raw carbon fiber, and we use a woven sheet, like the picture you can see on the right. And then the other part of the composite is the epoxy, which in our case is a two-part glue. This holds the carbon fiber sheets together. For manufacturing, we layer these sheets on top of each other, and often we vary the weave direction, and then we use vacuum pressure to help cure the epoxy that we mix in between these sheets. A ply is a single sheet of this carbon fiber material, and then each ply has a different weave, which is the pattern and orientation that those carbon fibers are woven together. The composite is the full plies that are stacked on top of each other with the epoxy to make the final material. Material properties of a composite, specifically carbon fiber, are a little bit different than most materials. They carry fiber most in their fiber direction, so along those specific each carbon fiber. And then it's reinforced with the epoxy. Carbon fiber is lightweight, stiff, and then you can vary the weave directions to optimize the strength, and that's what this project focuses on. For a carbon fiber layup, we are going to take different plies, like I mentioned before. So we have the 0-90 orientation, and then we can lay a 45 orientation, then a 0-90, and then a 45 on top of each other, and that's a 4-ply composite. And varying those weaves is what I look into for the rest of the duration of this project, and what I'll be going into in more detail. Michigan Electric Racing composites, as I mentioned before, you can see that the composites of the aerodynamic components of our car, or the outer surfaces, those are less structural though, because we have a steel chassis frame beneath it. The structural composites include the steering wheel, the pedals, the steering column, and the seat, and those all have to be really strong, but we want them to be light, which is why we make them out of these carbon fiber composites. As a little bit of more background into why I chose this capstone project, I took a lot of composite structure classes at U of M, and it became something I was really interested in. I was interested in the strength and material properties of these components and how they can apply to our design. And I just had a personal interest in figuring out the material properties and part optimization that come with this. Also, I was really involved in the past manufacturing for Michigan Electric Racing, and we didn't take that much consideration into the strength of our components or the weave orientation to optimize them. And I'm looking to get a significant strength increase with alternating weaves, and I know that our team is able to accomplish this, and I want to help push them into that direction. My faculty advisor for this project was Professor Heath Hoffman. He's the Michigan Electric Racing faculty advisor and our MDP course coordinator. Initially, my capstone project plan was to do a lot of physical testing. I wanted to manufacture samples of different composites with a lot of varying weave orientations, so 0, 45s, also including some 60, minus 60s, in a lot of different patterns, and then conduct physical testing with a 3-point bend test on all these materials to see how the strengths of them compared to one another. I wanted to develop a data book for the Michigan Electric Racing team to see which materials were the strongest so we could manufacture with those in the future and reduce the weight of our components. If we can make our components stronger with less material usage, they will then be lighter and better for the optimization of our team. I wanted to also offset this with some simulation softwares so that we could validate which orientations we were using in the software before we manufactured it. I wanted to verify the component simulation with some additional physical testing so that way I could correlate the results I was getting from the simulation and the physical testing results. Unfortunately, Corona hit and I couldn't do any physical testing. So instead, I developed an updated project plan that was mostly based on simulation alone. So throughout the year, I had been learning the simulation software to align with my initial goals, but I grew this to a larger goal of doing further simulations of composite components for our team. I also then decided to develop documentation for the simulation software that I was using to teach other members of Michigan Electric Racing so that way in the future they could be running as many simulations as I did this year. I did develop the testing plan for the physical composite testing that I wanted to conduct, and I'm hoping that in the future additional Michigan Electric Racing members will be able to run this test and validate the data that I hope to collect. I also started to explore FiberSims, which is another composite software, and I wanted to explore its applications to our team and develop introductory documentation as a team resource as that as well. I spent a lot of this year learning how to use Creo software to simulate composite structures. I was taught Creo initially by a student on a different build team, and they taught me how to establish my part geometry, my material properties, all in Creo. So in Creo, I'm able to model my part in Creo CAD, and then establish the different composite properties as well as the ply orientations. Like I explained before, I can define a 0 ply, and then a 45 ply, a 0 ply, and define all of those so that way it will be the same way I'm manufacturing my part in real life. I then define my loads and constraints of what conditions that the component is being put under, and I can run my simulations and analyze my results. These are a few components I was able to run throughout the year in Creo. So we have the steering wheel, and then in the middle there's the accel pedal, and then on the right is the steering column. The accel pedal snapshot shows a little bit of how the modeling is shown for the part with the constraints and the loading, and then the steering wheel and steering column show some of the results that I was able to get from Creo. For the steering column and the acceleration pedal, I was modeling a composite tube that we are going to be purchasing because I wanted to make sure that this tube was strong enough to withstand the loads that both components were being put under. So the steering column was simulated with pin connections, and I applied the steering torque to the column, and I verified that the tube could support these loads. For the acceleration pedal, I simulated the foot force on the pedal and the spring loads for the retraction, and I verified that this tube also could support the load. Both of the images on the right show strain across the components. So the strain is the failure method for composite components, as the strain must remain under 0.017 in the components. So I analyzed that and could see that the max strain of the part on the right for the steering column is 7.18 times e to the negative third, which is much under the 0.017, therefore this component passes, and that's how I was able to analyze the results that I was getting. The steering wheel analysis was a little bit different in that I was developing the ply plan for the orientations that the steering wheel would be made out of. I was hoping to optimize this plan to reduce the amount of carbon fiber that I needed to manufacture the component, but still make sure that it was strong enough to withhold the loads that we would be putting it under. My initial design had 18 carbon fiber plies, so 18 individual layers. I loaded this with the steering torque and the full driver weight leaning into the wheel. Through optimization, I was able to optimize down to 10 layers, and this material was still strong enough to withhold the strain. You can see that the strain of the 10-layer component, which is the bottom row, is asymmetric, so you multiply that I show out by 2. The strain is 0.009, which is much under the 0.017 that I said was a failure rate, with about a safety factor of 2, which is what I was designing for. I also was able to cut weight from the initial 18 layers to the 10 layer, and it's a weight savings of about 50%, which is pretty significant in our vehicle. From this experience simulating different parts for Michigan Electric Racing, I developed a Creo user's manual. I documented my abilities to use Creo between modeling the CAD in Creo, defining the material properties and the loads and the constraints, so that way other members can run simulations in the future. I outlined all of this into a large document, and hopefully team members can follow along as well as reach out to me for questions in the future. I was the only one that simulated parts in Creo this year for Michigan Electric Racing, and I don't want the knowledge to leave the team as I graduate. So I'm hoping this will provide clarity and make sure that they're able to still simulate software and build off of what I was able to learn this year through this Capstone project. The guide is currently at 28 pages long, and I've been reviewing it with some team members for feedback, and my plan going forward is to have one team member walk through the entire guide and make a part to see what other gaps I'm missing and fill it out before I graduate and lose my ability to use Creo Cane software. Ideally, I would be able to validate all the simulations that I've done with some physical testing, so that way I can prove that the simulations I'm running align with what we're experiencing in real life. Unfortunately, because of the coronavirus, I wasn't able to conduct any of these physical tests. Still, I developed a physical test plan similar to that would have aligned with the initial Capstone project goals. I couldn't conduct these physical tests, of course, like I've explained, but I'm hoping that someone will be able to run these tests later and validate my simulation software. My plan for this tests are to manufacture 12 different composites with different laminate orientations. So the 0, 45, 60s, all of those. I'm then going to conduct 3-point bend tests of the sample, and the picture up the right shows a 3-point bend test with an aluminum sample. This will evaluate to the load to failure, and we can determine which pieces are the strongest based on how much load can be applied before they break. All of these samples will be simulated in Creo, so I can correlate the load that they can support in Creo with the physical test results. I developed the Creo Simulation for this test, where I made the strip and did a sample ply pattern, and then I applied a point force in the middle to be the point force of that 3-point bend test, and then constrained the two edges similar to how they are constrained in that diagram that I had on the previous slide. The component on right is shown to a point of failure of a strain of 0.017, which, as I mentioned before, is the failure strain for composite components, and that corresponds with a load. I'll compare the simulated loads with the physical test loads to see if they correlate, and then people can improve my sims from there. Unfortunately, I won't be the one actually doing this test, but that's the overall testing plan. The final part of my capstone project was introducing myself to FiberSims software. FiberSims is a Siemens software that is also used to plan composite manufacturing work. I can determine the ply geometries from the CAD of the part, and then also to use that to develop my manufacturing plans. No one on Michigan Electric Racing has ever used this software, but it's always been on our list of things to do to improve the team, so I thought I'd take a crack at it. I've been working with the Siemens Supply tutorial to teach myself the software's abilities, and then I've been developing a user's intro guide for the team. I'm hoping to just shorten the learning curve to using FiberSims. I recognize that I can't make that much depth into the software this late into the game of the year, but hopefully the work that I've put in, where you can see that I've been able to lie some plies down on a part, will help jumpstart other team members to using that and improving our team in the future. From this project, I've been able to grow a deeper understanding of composite structural analysis. I learned more about the failure methods for composites and also how to analyze the different ply patterns and how they affect material properties. I worked a lot with the softwares, and I have a much better sense of how to use those and how to dictate my design based on the conclusions I'm able to draw from simulation softwares. I also experienced developing legacy documentation for the team. It broadened my understanding of what details are important while I'm learning some softwares to write down and pass on, while also strengthening my personal understanding of the software. There's still a lot of remaining work though, as I wasn't able to do any physical testing. So I want to finalize my Creo user's guide and continue to grow my FiberSims introductory documentation, but mostly I want to support the team of Michigan Electric Racing on their composite structural designs and manufacturing in the future. I want the team to be able to run my tests and validate my simulations and do all the physical testing that I wasn't able to do this year. Lastly, I just need to give a big thanks to Professor Hoffman to being my support and my advisor for this project, for the honors department, especially supporting us when all the work went virtual, Diego, who taught me how to use Creo, and Sean and some other members of Michigan Electric Racing for supporting me throughout my project.